One of the benefits is selectivity. So we can really leverage the mass-based specificity of the technique, selecting a specific surrogate peptide which we can only liberate from our target and not liberate from the background proteome. Then another benefit that we have is that we're less reliant on capture agents. So obviously we need to take a stock of what kind of LLOQ we require, and if possible, we want to keep the assay design as simple as possible. So if the LLOQ that's requested is high enough that enables it, we can simply resort to a total digest style approach where we just digest the entire sample and monitor for our surrogate peptide. However, if we need to reach lower LLOQs and we need a more sensitive assay, we can resort to adding immunocapture steps, so protein level cleanup, and designing a hybrid LCMS approach. So the kind of benefit of the technique is because we're less reliant on antibodies, that being we only need a single capture reagent, we don't need a second detection reagent, and then also we don't need, say, as good a quality of a capture reagent, so say it's less specific. What we can do is use that mass-based specificity to make up for that shortfall and kind of still use those lower quality antibodies. One of the great benefits of the approach is the scope of the targets that I can look at is not limited by the capture reagents that are, say, commercially available or can be provided to me. Say another benefit is I can set up a total assay, so free and bound, using the simple total digest approach where I indiscriminately digest all the material that's present. I can both monitor free and bound, looking for the surrogate peptide which is shared throughout the different scenarios. Another aspect is that the assay design is highly drug tolerant. So because I'm using that indiscriminate digest, as long as I liberate that surrogate peptide and it's not found within the dosed therapeutic, then I can differentiate. And then say finally, another benefit is I'm able to differentiate between isoforms without having to resort to very specific capture reagents because I can select a specific surrogate peptide which is only found in that isoform, which then allows me to differentiate. One of the main drawbacks is, of course, sensitivity. It is a limitation. However, if we take a kind of standard scenario where the dose therapeutic is going to capture the biomarker in question, and then we're going to see it adopt the half-life and increase in concentration, then protein LCMS approach really does become available again. Say another downside is these assays are quite complex to develop, so you're often using a bespoke assay design, so you need a lot of experience to build the assays. And also, because these designs are bespoke and they are, say, more complicated, you often resort to, say, non-standard approaches, so whether that's using technology like automated immunocapture using Kingfisher instruments, or whether you have to use technology like high-resolution mass spectrometry, 2D LC, or even microflow LC. One assay that we've recently developed is to measure total IgG and the IgG subtypes, so IgG 1, 2, 3, and 4, all in the same assay from human serum by protein LCMS. And the reason why we're doing that is because our client is interested in measuring the levels of total IgG and the subtypes in response to dosing with a biotherapeutic, which is designed to decrease those levels. So the reason why we chose protein LCMS for this approach is because that dosed biotherapeutic shares a lot of similarity with the endogenous material. And because we're selecting specific surrogate peptides, which allow us to distinguish between the endogenous material and the dosed therapeutic, we can accurately quantitate those endogenous materials. Whereas, say, if we took an immunoassay approach, we may see some overestimation of the levels. So the assay is set up so that we monitor a specific surrogate peptide for each of the different subtypes, and then we monitor one surrogate peptide, which is shared amongst them to give us our total IgG assay. And The whole assay itself is actually relatively simple, so we're not relying on any sort of capture reagent, and we just simply do a high temperature rapid tryptic digest. That last development was actually quite challenging. So because we're monitoring 5 separate analytes within the same assay, we're multiplexing, which is obviously a massive benefit, but it does come with some additional challenges. So the 5 analytes that we're monitoring, they're actually present in quite different concentrations endogenously. So everything from greater than 12 mg per mil to less than 1 mg per mil. So we need to balance that response. And we did this in a number of ways. So the first way we did that was by carefully selecting our MRD, so our minimum required dilution, and that's to make sure that we were able to dilute the samples into the range of the assay, but not so far that they were not able to characterize the mechanism of action of the biotherapeutic. The next way that we were able to balance our response was by optimizing our mass spec parameters. So we selected very carefully the parent and fragment ion transitions that we monitor for each analyte. So for the lower concentration endogenous analytes, so IgG3 and IgG4, we selected the most sensitive transitions. And then for the more concentrated, the higher concentration analytes like total IgG, IgG1, and IgG2, we selected less sensitive transitions. And then finally, we applied design of experiments approaches to optimize the digestions, especially for IgG3 and IgG4, so maximizing the response for those lower concentration analytes, whilst still getting sufficient sensitivity for total IgG, IgG1, and IgG2. Another difficulty that we encountered was when we came to assess parallelism, we weren't able to reproducibly demonstrate parallelism in the surrogate matrix we'd selected. That meant that we needed to identify a replacement surrogate matrix for the assay. And that was a little bit more difficult because we had a number of restrictions. So because we're monitoring an endogenous analyte, we need to make sure that it's not going to be, say, generated, the surrogate peptide we're monitoring, from that surrogate matrix. So we need to be careful in what surrogate matrices we select. Another kind of limitation that we had was we needed to demonstrate a nice linear response over our calibration line. We, of course, need to demonstrate parallelism. And another thing that we wanted to do was maintain the assay design and setup that we'd optimized. So we want to make sure that the surrogate matrix is allowing us to be similar, representative of our diluted unknown samples or our endogenous samples. So what we did was we screened a number of surrogate matrices, and luckily we were able to find another surrogate matrix which fit all those criteria. And we, of course, at that point, then needed to build our confidence that we were able to not see any sort of lot-to-lot variance. So we demonstrated that we're able to generate new pools of that surrogate matrix, and luckily that all went well. So after that, we proceeded to validate the assay, and now we're in sample analysis. So we've analyzed a large number of samples with a very high pass rate, so the assay is performing really well.